Okay, well, I want to thank Sam for creating an extra page and also blame him for being up here late. So I want to talk about concrete mathematical incompleteness. And for those of you who haven't heard my propaganda, I'll give a little bit now. So this has a potentially enormous potential for the future. Namely, that we might be able to have incompleteness from ZFC, which is sufficiently gripping to the typical mathematician that it changes their personal relationship with their field, with the field of mathematics. I know of story after story where a typical mathematician went into math because the rule books don't have to be consulted and altered as they have to for almost any other subject. In other words, the rules of the game don't change. It's just a pure challenge. And they like that feature of math, and many of them claim that that's what attracted to them in math versus other things. That there's no issue about what is a real proof. And of course, if you have incompleteness, then the issue of what's allowable resurfaces. If you have incompleteness from the standard rule book, then the issue of what's allowable surfaces. And so now I don't know of any other branch of mathematics at this time for which it is a realistic possibility that you could do something which would go after or change the relationship across the board in the field, the relationship of many people with the subject in the first place, the fundamental relationship with the field would change. It's hard to believe what in mathematics would do this other than the proper development of the Gödel incompleteness phenomenon. It's hard to imagine. I mean, you can imagine the Riemann hypothesis gets proved. You can imagine that manifolds get classified better. You can imagine transcendental number theory proves E plus pi is transcendental, all that stuff. There's no way that that's going to fundamentally change the relationship, the personal relationship of the mathematical community or a large fraction of the mathematical community with their subject. It doesn't seem to be enough to do that. So anyways, so I got attracted to this 45 years ago and decided that the proper development of Gödel's incompleteness phenomena was worth the agony and the ridicule. So that was the idea. Ridicule, of course, is an exaggeration. What I really mean by that is people saying, well, we already know that we have statements that are incomplete and statements that are independent, and people have adjusted to this and they haven't changed their attitude towards their subject, blah, 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 and all that kind of stuff. And besides, this was all known in the 1930s, right? So you have to listen to this as you proceed. But then maybe 45 years later, you don't get quite the same skepticism. Maybe perhaps you get people who express a lot of skepticism a little bit worried they were wrong. That's what you actually start to see. Now, in the process of doing this, I do touch base with a lot of different kinds of mathematicians, just to see if I'm moving in the right direction. And some of them are typical, ordinarily good mathematicians who do sometimes spontaneously express the fact that they want it's a very much part of their mathematical life that the rule book does not have to be consulted, and there is some sort of rule book out there that they don't want to worry about that was handled by strange animals called logicians. This is fairly typical. But I also talk as well to Fields medalists or equivalents about this. And usually I'm disappointed that I don't get as much insight from this as I hope, because it's very hard to keep their attention on anything because they got their own stuff. But many of the very leading mathematicians think of mathematics as an open-ended subject for which the existing mathematics that's done is to some extent historical accident and also temporary. And that mathematics, they have a broader conception of mathematics and what mathematically fundamental means that transcends exactly what the current structure is, which is something that I need in order for me to be taken seriously, because otherwise people will just measure the thing by how strong are the actual connections with actual things that are done. Now those connections are getting somewhat stronger, but that's not the biggest strength that it has yet. That's not. But of course, one tries to do that. I find that when you go to very well-known mathematicians, somewhat below the most creative and most decorated ones, you find that they generally think of mathematics, or serious mathematics, as what these superior people to them, or higher ranking people to them, that I just was talking about. Mathematics is what those people do and what they have suggested to be done, which they did and got careers for. So you have these people who are too high to think that the existing mathematics is a measure of what real mathematics or fundamental mathematics is. They're too high to think that. And then there's the people who made careers from the approval of these people, who definitely think mathematics is what these guys do. So now with these people, I can't even get in the front door very easily. They say, well, I never heard of that definition, and then that's the end of the story, right? And then of course, so now the objection can be made inside logic. There's a lot of vested interest in this not working within logic. And here is the main people that are against the idea of this is the set theorists. The set theorists think that this act like this badly reflects on them, because they're doing incompleteness in the tradition of Gödel's set theory stuff and Cohen, and they're doing this, of course. Everything they're doing involves pathological objects, which I'm going to discuss a little bit. Pathological objects in a precise sense and also semi-precise sense used by mathematicians. And they know intrinsically that they don't have any techniques whatsoever to deal with anything that doesn't have seriously pathological objects in it. So if this is the new standard, that the incompleteness has to now, the modern incompleteness has to now direct itself to situations where pathological objects don't enter. If that's the new standard, then they're actually back in school as freshmen, okay, after having distinguished decade careers. Now that's usually considered a pretty bad drop, to go from being on the top of some sort of area of logic all the way to essentially being nobody, absolutely nothing, having done nothing of any significance. So that's a big drop, and they tend to not like to want to do that for some reason. So they're not going to be very supportive of this. And I think that most of them not only hoped, but surely would bet that this was going to go away 35, 40 years ago when it was only 5 or 10 years old, my work on it. Okay, so we certainly have that. But this is an actual example of really going after and going back to original purposes. And that is also something that a lot of the logic community is bothered with, because by that standard, how many people in the other parts of logic have gone back to the original roots and purposes of the field in a general interest manner? There's a shortage of those people too. And if that's the standard, then a whole bunch of other people are going to go back to having no career. So you have to understand that I'm not the most popular person in logic today. Okay, we have to understand that. All right, so with that little summary, I'm not going to go through all this because it looks like what's happened to me is this. I have about 5 or 6 or 7 ways of doing this that's state of the art, that's beyond what was done in Boolean relation theory in various ways. And they were all competing with each other, and I couldn't figure out which is better. And then what always happens is, when this accumulates a lot, there's some 9th way of doing it, which is clearly better than the other 8. And therefore, the other 8 go into archives, and we proceed again until it happens again. That's been going on for 45 years, so this is no exception. So now, you know, there's a danger. I wouldn't recommend that everybody try to work this way, because then what happens if you have some sort of fundamental error going on, and at some point you wind up at the end of 30 or 40 years with absolutely nothing that's correct, and anything that was correct was never written down. So that's not a good thing either, right? So one has to be careful. But there is this, you know, there is stuff that's been carefully checked that I do. In other words, I actually do some things that are correct. Okay, so let me tell you, there's 2 things now that I think are state of the art. Arguably only 1, not 9, but maybe 2. I found a playground in the integers that really feels like a new combinatorial playground, just of the kind that logically oriented combinatorially oriented logicians would eat alive and build up into a big subject. That's very attractive, based on only one intriguing definition, which, by the way, I think I can actually get rid of an inequality in it and make it even more simple, though that hasn't been checked. I believe that's the case. That does a magic amount of incompleteness. It's a playground, meaning that you can't argue that it's overwhelmingly compelling that you must consider this definition. But this is a very interesting situation. You have a definition with almost no structure. It's a very intriguing definition. You can play with the definition a little bit, and there's some other definitions, you know, that are very close to it and so forth. But you look at this little definition, and all of a sudden, a billion questions come to mind, of which I considered a few, and all of a sudden you get very, very quickly to incompleteness from ZFC. So this playground, I think, is a permanent value. I don't want to throw it away. So I think that should remain, and I will talk about the playground in a moment. And then the second thing is what looks like an overwhelmingly strong, a very strong improvement, which is highly strategic. The highly strategic one is probably going to lead to a new paper. This time I'll actually publish it, called maximal functions and incompleteness. What I'm probably going to suppress or put as a footnote is this other development, in which I looked at sets, and I looked at maximal sets, and I proved that there's always going to be a maximal set that is suitably invariant. But in order to pull this off, I have to go through a few notions of invariant and cherry pick one out. And cherry pick one out that needs a little explanation. It's not bad and all that. And then I have my incompleteness. But with this new approach, It looks like if instead of sets I use functions, which I don't regard as an improvement, but it might not be, from many points of view, not bad, because there are a lot more functions in mathematics than there are sets, usually. And so, at the cost, which may not be a cost, of going to functions, I prove that there's a maximal function in which the value at two specific places are natural numbers. And the places are the two unit vector are 0, 1, 2, 3, and 1, 2, 3, 4. That's not bad. And then of course you can immediately say we have a calculus which asks which statements of this form, you can obviously talk about these statements, that values at certain arguments or lie in certain finite sets. You can ask, what is this in general true, and so forth. It's so-called templating. So I'm excited about this as a possibility. So I'm going to do the compromise in this talk. I'm going to talk about the playground. I'll call it the positive integer playground, which has its own attractions, and which is, by the way, seriously close to Boolean relation theory with some differences. But it allows you to make explicit pi01 sentences. It allows you to do pi01 things, whereas Boolean relation theory did not naturally allow you to do anything pi01, or even explicitly finite was a problem in Boolean relation theory. One knew that one stuff was equivalent to one con in theory. So this is a big improvement over Boolean relation theory from that point of view. And there's also some nice connections with chemistry. That are theoretical chemistry that are motivating. Now, which are pretty superficial, but you might be able to do much more with. Do some more advanced chemistry. Okay, so that playground I still think is good. And then there's this highly strategic maximality stuff. So there's always a maximal function satisfying a constraint. If you have any nice constraint, if you have any nice tame constraint, if you have a nice constraint, you can find an order invariant constraint. You can find a maximal function realizing it where the value at two vectors is an integer. Sounds like it's almost interesting, right? Okay, so this is general talk about the incompleteness business, which you don't need. All right. Now I have a little bit of philosophy here. Mathematical logic. What is mathematical logic? I've never heard it defined very often. Mathematical logic is the mathematical investigation of the fundamental structures that arose in FOM in foundations of math. Mathematical logic mostly adheres to the technical development and technical elaboration of the fundamental FOM structures. It is usually divided into 4 areas in alphabetical order: model theory, proof theory, recursion theory, and set theory. Naturally, the technical development and elaboration of FOM structures does not lead to general intellectual interest. Thus, 1 through 5 has been followed by a long period of decline in general intellectual interest. General intellectual interest, it means how close are you to everybody? Everybody on the planet that has a brain is interested. Okay. Now, the physicists have had a kind of a monopoly on this kind of thing, in the hard sciences, by asking questions like how old is the Earth, and is the sun, how old is the sun, when is the sun going to burn out, and there's a huge number of people interested in those questions, right? So this is the kind of thing we're talking about. However, there have been sporadic highlights. They've been generally obtained through a return to original seminal issues from FOM. Such return is generally obtained by these processes, alone or in combination. critical examination of relevance of structures being investigated, a refinement of the structures being mathematically investigated in light of FOM purposes, formulation of new kinds of questions and new kinds of results about the existing or refined structures. In this talk, I've only time to briefly discuss only some of the returning to FOM issues that hold great promise for the future, and of these, concrete mathematical incompleteness is the most ambitious and challenging. And then I have a section here on pathological objects. Pathological objects play a far greater role, continuing role in mathematical logic than any other area of math. I think this is true. At least in any other respected area of math, I think this is true in the sense of being represented in major math departments. But what is pathology? It is better to think of natural descriptions of objects. Another way of making this point is that the other areas of mathematics are largely driven by critical examples that are given by natural descriptions. Hilbert space, and so forth and so on. The area of math logic, complex field. The area of math logic that has the strongest focus on the pathological is clearly set theory. Already arbitrary sets of real numbers and arbitrary sets of countable ordinals are way off the charts when it comes to pathology. To get anywhere near the level of non-pathology now customary in mathematics, we must go down to Borel measurable sets of real numbers, or in Polish spaces. And even Borel measurability is at the outer limits. The first few levels of the Borel hierarchy is far more congenial than higher up. But even here, one should not overestimate just how reasonable the objects are from the viewpoint of the math community. We arguably begin to depart from normal mathematical thinking when we consider arbitrary point-wise limits of continuous functions from R to R. These are the so-called Baire class 1 functions. Baire class 2 functions, point-wise limits of Baire class 1, will generally cause considerable pain. Descriptive set theory is the part of set theory that pretty much lives in the Borel measurable world. It has far more points of contact with the rest of mathematics than it does the other parts of set theory. Given the special status of incompleteness discussed in section 1, the following question becomes crucial. Does incompleteness rely on pathological objects? Is there a statement involving no pathological objects which is independent of ZFC? The investigation of this question is the greatest motivator of concrete mathematical incompleteness. Other areas of mathematical logic suffer from reliance on pathology or lack of natural descriptions. In recursion theory, there has been a huge long-term investigation of the Turing degrees and the RE sets, both of which came out of fundamental investigations in FOM. The RE sets that are not recursive and not complete were extensively studied. To this day, no even remotely natural example of such has ever been given. In fact, it is generally believed that there are none, although no one has a reasonable formulation of such a result. Similar remarks apply to the Turing degrees and more modern reducibility notions. In set theoretic model theory, essentially arbitrary structures are investigated mostly with the lens of predicate calculus. Although more presentable descriptions arise here than in set theory, outside of descriptive set theory, the focus in set theoretic model theory is entirely away from structures of the kind the mathematical community is concerned with. The part of pure model theory that comes closest to being mathematically normal is countable model theory in pure model theory. But even here, this is at the outer fringes. Finitely generated structures are much more mathematically attractive. On the other hand, various topics in applied model theory have been directly motivated by various areas of mathematics and consequently do not rely on pathological objects. Mainstream proof theory does not rely on pathological objects. There are also topics in applied proof theory, again directly motivated by considerations in various areas of math where pathological objects play no role. Discussion of the pervasive reliance on pathological objects in mathematical logic has been taboo ever since the mathematical community disengaged from them in the second half of the 20th century, meaning disengaged from discussion, I think is what I meant. The general feeling in the logic community was that acknowledging this issue would be of incalculable damage, as so many celebrated results, including incompleteness, would be severely affected. However, concrete mathematical incompleteness and other developments point the way to a much more powerful and relevant form of mathematical logic. Now, I want to talk about just a few return to FOM issues, not meaning to be complete. Reverse math and the strict reverse math. The first was founded by us in the late 60s and early 70s, now generally accepted by the recursion theory community. The techniques used are predominantly from recursion theory, with some techniques used from proof theory, and a little bit from general model theory and from set theory. RM and SRM were invented by a re-examination of the role of formal systems generally. I was sick and tired at the Stanford T of people almost laughing with derision when I told them that I work with formal systems. What good is a formal system? There used to be old jokes about a formal system as the most ridiculous thing to ever study. So I started to think that maybe I ought to prove that they were actually equivalent to mathematical statements, right? That might help matters. Okay, so and some particular formal systems from FOM, specifically proof theoretic incompleteness. I don't know what's the specific, I think, specifically. Oh, I see. The role of formal systems generally and some particular formal systems from FOM specifically. Yes. Okay. Proof theoretic incompleteness. This is the use of ordinal notations for incompleteness. This started with Gensen. It was applied to combinatorics by us, the Kruskal's theorem, Higman's theorem, and the Graf-Minor theorem. It was integrated with phase transitions in combinatorial analysis by Weiermann and others. Interpretation theory. The foundationally crucial notion of interpretations between theories is investigated with foundational purpose. This was initiated by Tarski. Major impetus with our theorem that it essentially establishes an equivalence between relative consistency and interpretability, and a joint book with Visser is planned. I can prove that it's being planned if you tape record our lunch conversation. In fact, it's a very important issue in this book, by the way, it has to be handled with great finesse, is what definition should we use for what an interpretation is. I know it's pretty strange we're going to write the important book on X, and we've got to spend all this time figuring out what the definition of X is. This is a little bit unusual, but you understand. Insiders know what we're talking about. Okay, concrete mathematical incompleteness. This project grows out of the realization that pathological objects play an essential role in current work in set theory. This can be traced to the work of Borel determinacy. Tame model theory. Surprisingly fruitful conditions are placed on the definable sets in one dimension, e.g. O-minimal, minimal, strongly minimal structures, Van Andries, Pillay, Steinhorn, Baldwin, Lachlan, and others. Applied proof theory. Use of proof theory to obtain uniformities and estimates in a uniform way using proof theory arising in FOM, such as cut elimination and Gödel's dialectic interpretation. Kreisel and Kohlenbach are two of the most closely associated with this. Okay. Now, the current state of concrete mathematical incompleteness. The examples are quite simple, easy to understand, and well motivated. They'll get somewhat more simple, somewhat easier to understand, and somewhat more well motivated over the next year. And already this has happened, this morning and last morning. Okay, so exactly this. Okay. After that, the next big step will be for the examples to make the jump to at least a few standard mathematical contexts that are in broad use. So instead of looking at maximal functions, I might want to look at maximal continuous functions in some space, or something. Who knows? Or maximal analytic function. Who knows? But it's hard to anticipate when I can make the jump and how I'm going to make the jump. But I'm going to try to make the jump. For this, I have to incorporate standard mathematical structure rather than have statements that employ virtually no structure at all, as they do now. So right now, I use no structure. I don't consider less than on the rationals a profound, complicated mathematical structure. That's all I'm using. Okay, with my integer playground, I'm using addition and less than on the positive integers. This is also not a profound, typically profound, complicated structure in mathematics, right? This is very elemental. Conway, Pfefferman, Furstenberg, Gromoff, Mann, Maser, Mumford, Nelson are names of people in recent years I've had serious discussions with who are at the level of mathematics is a broad subject that transcends what me and my buddies are doing. These people. Generally speaking, the work is accessible enough to have extended one-on-one conversations with these people. Now, there's an interesting phenomenon, and I told you about this, I won't repeat it. As I said, ultimately, issues of naturalness and relevance will recede in importance as incompleteness is shown to be present anywhere there is substantial structure. So here's my conjecture. Anywhere in mathematics where there's substantial structure, there's completely, totally friendly, mind-bending incompleteness, which severely affects the relationship of mathematicians with their subject in a personal way. That's the conjecture. All right, now here's the playground, the integer playground. Some base towers are rather easy to define and have the look and feel of being combinatorially fundamental. My 48-page abstract, I give the definition early, but I also give it slowly with motivation. So I try to have my cake and eat it. You got a longer story, which is tightly motivated, and you can complain about how smooth the transitions were, or you can just give it all at once and say, here's the playground. So one way of doing it is to literally build the playground from scratch. The idea of actually having, so here you have this room you're going to build. One way to do it is, first you're going to say, we need a chair. And you bring in a chair. Nobody complains about having a chair. Then we need 2 chairs, okay? And you bring in a second chair, and then and they match pretty well. You know, maybe one chair is small and the other's a little bigger because there are going to be people of different size in there. Then you bring in a table, and you say, well, you know, they want to rest their, you bring in about 4 or 5 pieces of furniture like this. Okay, the other way to do it is say, oh, by the way, we're going to go to this, here's a playground, it's got 5 pieces of furniture in it. See, familiarize yourself with it, and then let's do something serious with this room. So those are 2 different ways to approach it. Now, I want to emphasize that even if I were to take the crude way of presenting the playground, just, the 5 pieces of furniture, just the crude way, that this would already be approximately 50 times simpler than anything one does in mathematics today. You try to teach somebody something. We're going to play in real analytic functions. We're going to play in real analytic functions is 50 times as complicated a room as what I'm talking about here, right? Okay, and so forth. Okay, so the strength of this stuff is a kind of fundamental simplicity. Now again, the second thing that I'm about to tell you, which is the thing of this morning, is heavily strategic. It also looks like a playground, but it's not presented as a playground, but it's presented as a mystifying secret that maximal functions under constraints are extremely deep and subtle matters, maybe profound, because it has a sound of being profound. Maximality means do as much as you can, right? So that's a different flavor. A playground versus perhaps something profound. A little different. Okay. So if I were to introduce this playground one piece at a time, I would construct 4 definitions. The first definition is the base of a relation. The second definition is a sum base for a relation, which is a weaker kind of base. And the third definition is a sum base pair, which is a staggered form of B. And the fourth definition is the real one, sum base tower, which is simply iterating a sum base pair. Each of these definitions give rise to a substantial theory. You can stop anywhere and do some interesting combinatorial work. It's only when you get to D that ZFC gets pressured. It's only when you get to D that ZFC gets pressured. Okay? Otherwise, you're only pressuring Ramsey theory and elaborations of regular Ramsey theory and so forth. Okay. So let me mention what these notions are. And we'll also give the definition at first. We'll see what happens. A base for a relation on the positive integers. They're unique. Now that already is a showstopper. If they're unique, they're probably going to be pretty interesting, right? Okay, so, and then there's a challenge for calculating them since they're unique. And there's a bunch of algorithmic decidability issues and some deep questions, that's not clear how to answer. So you can already spend a decent portion of your life in little a, though you're not likely to run into ZFC. In B, a sum base. These are not unique, and there are two unique notions. There's a thing called the rich sum base and the poor sum base, and they are unique. And they can be studied like A. Anybody who makes a life in A should make a life also in B, probably, at this point. And then sum base pair is a very important idea, offshoot of little b. And there's a substantial list of theorems using various Ramsey arguments, infinite Ramsey theorem for this, about sum base pairs. You can always find a sum base pair for any relation that starts where the ground set is made of only odd numbers. This requires some Ramsey theory. You even have to, just to show that you can get one where the first set is infinite is already a little tricky, but this is harder. So you already get some Ramsey theory. But then you can find a sum base tower of any length, a sum base tower of any finite length, starting with a set of odd numbers, equivalent to one consistency of large cardinals. See, so you're going way beyond ZFC when you do that. Okay, so now I'm going to actually present the full playground for you and see what it does for you. Okay, here's the full playground. First of all, you need a definition. N is R related to M1 through MK minus 1 if and only if R of N, comma, M1 through MK minus 1. That's what I mean by N. N is R related to M1 through MK minus 1. Because it could mean a number of other things, where the position of N might be in the middle somewhere. I need it to be at front, okay, in the front. Okay, so now here is the playground. So let R be a k-ary relation on the positive integers. A sum base tower for R is a finite or infinite sequence of sets. I only really care about the finite case, but you can talk about the infinite case too. Is a sequence of sets, A1 contains A2, is a tower of sets of positive integers such that the following holds. I usually normalize with 1 in A1. That's not necessary, but it does seriously lengthen some of the proofs of the reversals. So it probably is a good simplifying idea to insist that 1 be in the first set, in the ground set. Secondly, for every binary sum from the I set, either the binary sum is in the I plus first set, or it's related to some earlier numbers from the I plus first set, but not both. Now, you either immediately find this definition intriguing or you don't. And if you don't, I would go back to building it up with the components that I mentioned. But that's the playground. So here is the slow treatment. The slow treatment. By the way, once you buy into this definition, the game is over. Okay. So I'm just. The game is over. We have this beautiful, gorgeous development with all kinds of large cardinals swimming all over the place with tons of reversals and endless work. Okay. So you just have to buy this into this definition. All right. So. this statement is independent of ZFC, proposition 5.3. Now the slow treatment. So if you don't like the original playground, we do it a little bit slower. S is a base if and only if for every n is an S or n is R related to some m1 through mk minus 1 less than n from S, but not both. So this is a piece of chemistry, okay? In other words, positive integers are compounds, matter. And I want to build the elements, as in the periodic table, okay? And what do I need to know? I need to know that everything is either an element meaning chemical element, or can be broken down to broken down into elements. Obviously, I don't want both. You don't want an element is something you can't break down any further, right? So that's exactly what this is saying. Except the notion of constituent, molecular constituent, whatever, is given by capital R. Now, this is obviously unique. And it's a delicious recursion, right, that gives you the unique base. Okay? And as I said, you can go study this. I made some calculations of some basic R's, what the unique base was. You get these periodic sets with period k squared minus k, where k is the dimension. And there's also a nice one. If the relation is n equals m times r, then the unique base is the set of prime numbers together with 1. So there's some nice things there, and I claim some algorithmic undecidability results. You can't tell whether a base is finite or not, even if it's Pressburger relation, or an integral piecewise linear relation. You can't tell. But I don't know how many dimensions you need to have that undecidability kick in. What about for low dimension? Also, given two of these things, you can ask, do they have the same sum? They have the same base. And that's undecidable. And so forth. So there's a whole bunch of stuff like that. Very basic algorithmic issues that come out negatively because this is too powerful, this base construction, in the limit. A base is obviously polynomial time computable relative to R. That's not a problem. But the point is, you can't tell what happens globally with a computable thing like that. You can't tell whether it even is finite, and stuff like that. Okay, so one can do a lot of projects there. But now, what is a sum base? A sum base is the same as a base, except that you just require the definition to work for binary sums from the so-called base. So this is a weaker notion of base, that for every n in S plus S, either n is an S or n is R related to some lower things, but not both. So this sum base is a weaker notion, and you have more flexibility, obviously, here, because it's easy to give examples where there's 2 to the aleph, not many sum bases. It's also you can give examples where the sum base is uniquely the same as the base, and infinite. So there's situations where it's not more flexible than a base. You can also have that. What is a sum base pair? Now this is where the interesting action really starts. What is a sum base pair? A sum base pair is staggered. And I don't know the history of or analysis of staggering in mathematics. So somebody should write a paper, staggered mathematics. Because, there's a lot of mathematics that looks staggered to me. Where you have a tower of structures that are getting richer and richer or something like this. You see this kind of chains going on. Okay, so here you could do this chain thing. So what is a sum base pair? A sum base pair is a set together with a bigger set, such that if A was equal to B, this would just be a sum base. But it's weaker than that because it just says, see, if A is contained to B, it just says that if I have a binary sum from A, then it's either in B or related to K minus 1 things lower that are in B, but not both. Now, here is this tough theorem, serious theorem, just for sum-base pairs. Every relation has a sum-base pair starting with an infinite set of odd integers. And you really have to do, you know, do some significant argument with the infinite Ramsey theorem to have a chance of proving this. I mean, I didn't go into the reverse math of this statement, but you know, this already is an interesting theorem. By the way, there's a proof that there's always an infinite sum base. There's a proof that there's always an infinite sum base, and that proof is easy. Fairly easy. No Ramsey theorem really needed for that. You sort of build it for a while, and you hope that, you know, you build the full base for a while. Now, oh my God, the base might end, and then you're dead, right? But you were trying to get a base. Okay, at some point when it's safe, and you haven't for 50 million years put a number in the standard construction of the unique base, what you do is you slip a number in right there. And you can see that, in fact, if you think about it, that won't hurt anything. And every once in a while, when you get really upset after millions of years, you stick a number in, and you can get an infinite sum base pair that way. Okay. So you do the ordinary thing, and if you get too delayed, you slip a number in. Otherwise, you just do the usual. So you can show that works. But how do I know that all the numbers can be made odd? You see, there's a problem with that. You see, if I really have a lot of leeway for a long time, then I can just wait for an odd number. You know, I can just make sure it's an odd number put in. That's not a problem. The problem is when I'm really having something going, things are going well for me, and I am having to basically do the base. We know that a base may be made of only finitely many odd numbers. So we know that we can't just follow the base. So it's that intermediate level where there's a problem making infinitely many odd numbers in there. But you can actually do it. All right. Okay. So, but now, what about theorem 5.4 for a tower? What is a sum-base tower? A sum-base tower just means, so a sum-base tower just means that AI and AI plus 1 are a sum-base pair. So it's a sum-base pair, sum-base pair, sum-base pair, sum-base pair. That's all it is. That's the definition of a sum-base tower. It's the trivial extension of a sum-base pair. And then you can't do that in ZFC. The Ramsey tricks you need are just too much for you. You have to do the Ramsey thing in a side structure, which is a large cardinal, a well-ordered large cardinal. That's where you have to do the Ramsey theory. And you can prove that you have to. Now, what if the relation is tame? So I can hear you tame model theorists here. One of the countercultural people that are not here, by the way. I can hear you say, I don't care about this, Friedman, because it's not tame. So if R is tame, this actually is still independent. It's equivalent to con of large cardinals. Okay, if it's tame. And it's actually easier to prove it when it's tame, because then the lifting to the large cardinal is straightforward. The problem is lifting. The problem is when it's an arbitrary relation, you have to do some preparation via the infinite Ramsey's theorem. Now, those of you steeped in Boolean relation theory know that that's exactly what I did. I made some preparation, if you remember. In order to, in the proof of the Boolean relation theory statements, I need to make some preparation, you know, to do that. You know, you can, if you remember. All right, so there we have that. But this tame side allows me to get con. And then there are things like this, proposition 5.9. Oh, let me go back. If it's tame, so this is more advanced, one more step that I want. If you have a tame relation, then you can find arbitrarily long finite sum-based towers starting with an infinite geometric progression. 1r, r squared, r cubed, dot, dot, dot. And that is a theorem, and that's equivalent to consistency of these cardinals. Consistency. Now that has a finite form, a very nice finite form. That is, if you just want a, you can get, you could just ask for arbitrarily long finite geometric progressions whose ratio and length are sufficiently large relative to the dimension of relative to the dimension and parameters and presentation of the tame relation. So if I have a tame relation and I have a length of a geometric progression and a ratio of a geometric progression that are both relatively large compared to the presentation of the tame relation capital R, then I can do it. And the tower will be made of finite sets. I can do that. And in fact, now that's a pi 02 sentence or something, or pi 03 or whatever. And the fact that I can do that is equivalent to consistency of the large cardinals. And furthermore, I can give a double exponential upper bound on how big sufficiently large means there. So now we have an explicitly pi 01 sentence. Okay, and now there's something very interesting that happens. That's 5.9. There's something that's very interesting that happens when I go to multiple sums. Remember, I'm only using binary sums. When I go to, the only reason I'm using binary sums, I didn't want to overload your patience. So binary sums are, like free, right? Okay, but multi-array sums are really what's important. And if you use a free variable for the length of the multivariate sum, if you use a free variable for that, then the whole thing becomes independent for towers of length 3. A contained in B contained in B. C. In other words, A and B are sum-based pairs and B and C are sum-based pairs. The whole thing is independent of length 3. Now, those of you steeped in Boolean relation theory, remember the fact that the main Boolean relation theory statement is a length 3 statement. Okay, and then on the proof side, when I proved it was true, I actually got towers. You see, so this is a closely related subject with some differences. The big advantage here is that underneath everything there is the enormous flexibility of getting pi 01 and explicitly pi 01 is a big advantage. Okay. Okay, now here's a proof of something. You use the free abelian summing group generated by a well-ordered set of generators of type a large cardinal. That's how you actually do these things. For the tame case. For the untamed case, for the regular R case, you have to do this preparation with an infinite Ramsey theorem first. But eventually you're going to, no matter how you do this, you're going to eventually want to look at the free abelian semigroup generated by a big well-ordering and do stuff in there. Do large cardinal combinatorics in there. Okay. It dawned on me, I think I was technically in Ghent when this happened. It dawned on me that in that definition, I probably don't need n greater than m1 through mk minus 1. Remember I said either you're thrown in the set or you're related to lower things. How about you're thrown in the set or you're related to some things, but not both? Some things in the set, but not both. Now, we know that that's a provable simplification because all I did is rip out a couple of letters, right? Okay. I think that I can, I mean, I haven't checked this yet, but I think that I can show that you still get all this independence and all this incompleteness, even for that notion. Which is, I think, pretty surprising in many ways, right? I mean, that's just pure maximality without bringing in less than. So I think that's true, although I'm not for sure. Then what I did is I said, oh my God, then I can actually say this differently with functions, and maybe more mathematicians will like the playground. So let f be a function from n to the k into n. A constancy tower for f is a tower of sets such that f is constant all over the place. And for every n, for every binary sum from the ith term that's not in the I plus first term, if I were to throw that number in, I would fail to be constant. So this is a maximal constancy thing. And people do want to do this kind of thing. They like to have a function that's constant everywhere, or like to have a function that's well behaved everywhere. But they can't get it everywhere, so they look for a large place where it's well behaved. And that's what this is. So this leads to a whole subject of, now it's towered. It's towered. And we're now getting very fussy. But it's towered. But this leads to a whole subject of maximizing the places at which a multivariate function is well behaved. But it's towered. Now what I haven't gone back to is maybe just a fantasy, and I'll be again a little longer, just a fantasy, that maybe if I think this properly, that I don't have to, the Holy Grail is I'd like to have statements that don't have any tower in it. That's the last vestige of defense. Somebody can say, I'm a mathematician, but I hate towers. So goodbye, right? I mean, you see, a mathematician can say that to me. So, but it's possible now that I'm having more material in here, like a function being constant on a lot of places. Maybe there's a way for me to actually flatten this out with no tower, because I'm actually doing something a little bit more rich. So this thought occurred to me 5 seconds ago. Okay, so I don't really, even I won't make a claim on an idea that I just thought of while I'm talking, making the claim. So this is even too much for me. So I don't make any claim about this idea, but it just occurred to me. Okay, so there may be something coming up like that. Okay, now, I had a whole bunch of stuff I was going to tell you about, which is a variant of other stuff I was going to tell you about, which I think maybe I want to tell you about this instead. Okay. So this is, if this is right, this is clearly my best shot at something strategic to shake people up. Okay, we're going to work with partially defined functions from qk to q, where q is the rationals. Okay, somebody can say, I don't care about partial functions. I only care about functions that are everywhere defined, right? But there are things in mathematics, like complex variables. You want the function to be defined as much as possible in a certain direction, continue it as much as possible, and can't do it on the whole complex plane, and that's just one case. So mathematics does have this idea that you may not be able to do something everywhere. You do it only somewhat. You only do it as much as you can. Now, regular human activity very much has this idea. You try to maybe you want to make as much money as you can, right? But you can't make all the money there is, right? So your economic activity is only going to be partially successful, right, or whatever. You can bring in. In fact, you know what? Maybe I should just bring in real life into this, and then have that drive the subject. I mean, I'm very close to trying to make that move, right? But anyway, so here we have partial functions from q to the k into q, and now we view any relation, any subset of q to the nk plus n, as providing a constraint on f. A constraint. And what do I mean by realizing a constraint? To realize a constraint means I want that for every x1 through xn in the domain of f, I want the relation to hold of x1 through xn and f of x1 through f of xn. This is a very natural kind of constraint. You could look at more general kinds of constraints, but this is pretty interesting. Okay? And of course, you know, in a more polished situation where I'm convinced that I found the right holy grail, I would give you 18 examples from mathematics of constraints or something. You know, I'd give you examples of constraints. So a constraint is a constraint on arguments paired with values, right? A differential equation is a constraint. Right? Okay. A maximal realization of R is a realization of R that cannot be properly extended to a realization of R. That clearly is a good definition of maximal. Just the inclusion maximal for functions. You can't enlarge it. More generally, a maximal realization of R on a set A is a realization of R with domain included in A that cannot be properly extended to a realization of R with domain included in A. So I might be interested, for example, in only functions defined on the first quadrant of Q to the K, first octant of Q to the K. And so there's clearly a notion of what I mean by maximal realization on the first octant. It's defined on the first octant and it can't be extended staying in the first octant. Every order invariant constraint. Now I want to look at order invariant constraints. So this is the other idea. I'm going to look at very tame constraints. Order invariance is a very strong form of tameness. Order invariance, I'll give you two definitions. One is it only depends on the order, that as a set of tuples, it's order invariant in the way that logicians know very well. The other definition is it's first order definable in Q less than with no parameters. We know that these are equivalent. So every order invariant constraint has a maximal realization on Q plus that's actually no good. Q greater or equal to 0 is what I wanted. This passed through Sam. Not Q plus, Q greater or equal to 0. And I write Q, my Q greater or equal to 0, I write Q, the greater or equal to 0 as a subscript. It means the non-negative rationals. Okay. So maximal realization on Q, Q greater or equal to 0. I think I either know or strongly suspect that this is provable with Q plus. So the Sanders variant is not what we want. Maximal realization on Q greater or equal to 0 to the K, partially mapping, now SOME should be gone. Now, that might be my fault. Partially mapping the vector 0, 2, 4, 6, 8, dot, 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 2K minus 2, and the vector 2, 4, 6, 8, dot, 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 to 2K into the integers from 0 through 2K plus 1. Now, why do I use this partially mapping? Remember, the function is only partial. So the values at these two particular vectors might be undefined. So, here's another way of saying it. I can find a maximal realization on Q greater or equal to 0 to the K, where maximal realization F on Q greater or equal to 0 to the K, where F of 0, 2 through 2K minus 2, comma, F of 2, 4, 6, 8, dot, 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 2K, is a member of the set consisting of 0 through 2K plus 1, union, left bracket, undefined, right bracket. See, if I had more time to play around with how to present it, I might have, picked that. But it's clear what I'm talking about. Okay? In other words, I can find a maximal realization. Now, the reason for Q greater than or equal to 0, the reason for Q greater than or equal to 0 to the K instead of the Sanders variant is that the number 0 is a singularity that I need to possess in the reversal. I need the singularity. Also, by the way, it wouldn't have made any sense anyways, because the value of the first vector would have to be undefined if it was a Sanders variant. So we know that this was bullshit in the first place. Okay, all right. So it has to be Q greater than or equal to 0 to the K. All right. Now, I tried to do this without going to Q greater than or equal to 0 to the K. And you can, but I need a tower. I need a tower. If I have a tower of order invariant constraints, I can always find a tower of realizations with the same conclusion for each of the functions. The same conclusion. Same conclusion for each of the functions. Yeah. So, or the last function. You just worry about the last one. It's enough. And that's also nice. But if you try to do this without the singularity, I mean, if you try to use Q to the K in the first one, not Q to the greater than or equal to 0 to the K, you just use Q to the K, then I don't know that it's independent. That's open. I'm not sure. You see, that's my preferable one. That would be the simplest one. That would be the first one with only Q, or the second one for M equals 1. Now, I think the second one is independent when M is equal to 2. When M is equal to 2. And also, it's independent. I think the second proposition is independent when K equals 3 even. So you can have a very low dimension and a very low M. For the second one, the first one is trickier. For the second one, I think M equals 2 and K equals 3 is enough to be independent. And then the actual numbers are 0, 2, 4, and 2, 4, 6. And 0 through 7. 0 through 7. Now, the reason I can get away with this is because maximality in the rationals, you know, this gives me a second Turing jump, you know, a delta 0, 2 set, you see. Okay. And now the next problem is how do I give an explicitly finite form of this without passing to towers? Towers are fine, but, you know, maybe I want no towers. It might be better, right? No towers. And I don't really want to waste your time with this because I'm not going to do it quite right off the top of my head. But that's. But you should look on the FOM list, later next week, for this. So I think that we're in pretty good shape. We've got probably the first one could be a little bit better than the second one. Although the second one is the idea of a tower of constraints, having a tower of realizations. Once you get used to that, you find that very, very reasonable. Because it's like, for example, every set can be extended to a maximal set. You know, the usual thing. So before one buys into that, one has to talk about the first one, where you just have a single constraint. And the price I pay is not high. I just have to I just need Q greater than or equal to 0. The space Q greater than or equal to 0. And then it's open if I just talk about Q. And then we can also make case reasonably small, so we can talk about actually two specific vectors. Now this suggests, what about the general problem? What if I say I want my maximal realization to map this vector into this set, finite set, this vector to this finite set, this vector to this finite set, possibly union set consisting of undefined. In other words, if it's going to, or undefined. If I just, give you a list of stuff like that, I can ask whether this is a true statement. And I presumably could calculate that entirely using the large cardinals. tell you exactly when this statement is correct or not. And then you would have to use large cardinals to know that what you're doing is correct, because even this simple case, even with very small numbers, you can't do it without the large cardinal. And actually, this is consistency, not one consistency. And then now somebody might say, well, look, order invariance is too little. See, I make order invariance because it's so little. Order invariance is too little. Can you make the relation, can you give me at least some arithmetic operations, or can you give me something? Well, the answer is yes, but then the numbers are bigger. But what's wrong with big numbers? So I could write down, so if it's with plus and small dimension, maybe I need to write down 76 and 104 and 217 and 8,045. That's not so bad. That's fine. See, so I can accommodate more complicated constraints this way. So then somebody says, I hate the rationals. I only work in the reals. Well, I have some things for that too, I think. I mean, I'm not ready to announce. But we could try to make everybody feel uncomfortable. That's the idea. Universally uncomfortable, so that everybody is now, their personal relation with mathematics is being altered. This is what we want to try for. That's what we're looking for. Somebody might say, well, I only care about topology and manifolds. What is the geometry in this? Well, then I have some more work to do. I have to, these functions have to have some geometric property, and I'm taking max. So I think there's some core combinatorial thing, so that no matter what you object about this, the core combinatorial thing somehow survives. If you want the constraints to have more mathematical content of a certain kind, or the functions to be more regular or something, there's a core combinatorial content that somehow survives that makes it impossible to do this without going beyond the usual rule book. That's what I think is true. Okay, I'm finished.
Continue with the next presentation by Prof. And afterwards we will have